Hey there, I'm hiding behind a bunch of graduated cylinders. So before the weekend, I mixed two solutions in these graduated cylinders. One of them is a copper chloride solution. The copper chloride is just a beautiful blue solution. And the other is sodium phosphate. And sodium phosphate is totally colorless. And so on the ends, I have just sodium phosphate and just copper chloride. But then in the middle, I mixed them in different ratios. They all have about 60 milliliters total volume. And what's kind of cool is when the solutions react, they form a precipitate. So I let the precipitate kind of settle over the weekend and then just had fun kind of looking at which one made the most precipitate. Now, all of the solutions, I should say both of the solutions, the copper chloride blue and the sodium phosphate colorless, were both 0.1 molar solutions. So if I have equal volumes of solutions with the same molarity or the same concentration, there should be equal moles. So I decided then, just for funsies, to make a little graph and try to graph the volume of each solution used versus an approximate volume of precipitate. Approximate. Okay, so let me show you this graph. It might take a minute, but we should be able to find this graph. Cool. Okay, so here's my graph, this one. And I can make it bigger so you can see it better. Okay, so the balanced equation is as followed. There should be 3 moles of copper chloride plus 2 moles of sodium phosphate, forming 6 moles of sodium chloride, and then 1 mole of this copper phosphate. Now, you do not need to balance equations in this unit. We're just mostly focused on the ratios and the stoichiometry. In the next unit, we'll get more in depth with the different types of reactions and balancing them and all that good stuff. But here is the balanced equation. So we've got the blue copper chloride, the colorless sodium phosphate. Of the two products, sodium chloride should be a clear solution. It's salt water. So I'm thinking that this clear solution on top of some of these blue precipitates, maybe that's some sodium chloride solution. And then the copper phosphate, that's the blue solid. That's the blue precipitate. Okay, so I did not really officially graph the test, or I should say the graduated cylinder that's all copper chloride or all sodium phosphate, but I set them up here just so you could kind of see what the two solutions look like before we combine them. Then I just started mixing them. So I've got a ratio of, you can kind of tell, like on the graph, I had to put in, like they wouldn't let me put in both solutions. So I've got a volume of the copper 2 chloride. So one of them, this guy, wait a second, this guy is 10 milliliters of the copper chloride and 50 milliliters of sodium phosphate. Then this guy was 20 milliliters of copper chloride, 40 milliliters of sodium phosphate. This guy was 25 milliliters of the copper chloride, 35 milliliters sodium phosphate. This guy was 30-30, so equal volumes. Then this one was 35 milliliters of copper chloride, 25 milliliters of the sodium phosphate. And then this one was 40 milliliters of copper chloride and 20 milliliters of sodium phosphate, and so on. Okay, so then what I wanted to kind of do was look for the combination that gave me the most precipitate. And I found it to be this guy here. It was the ratio of 35 milliliters copper chloride, 25 milliliters of sodium phosphate. Now, if I didn't know the balanced equation and they maybe just gave me a graph, somebody was making a graph with differing amounts of these two solutions, and they might have said something then like, which ratio gave me the most product? Well, duh, I could just read the graph and follow it down. So the 35-25 combo seemed to give me the most precipitate. That's this guy. Well, now they might say, how does that ratio correspond to the ratio from the balanced equation? Which now here we see the balanced equation, and it's a 3-to-2 mole ratio. Of all of the ratios that I use, and I was trying to keep them pretty simple, that 35-25 is closest to the 3-to-2 ratio in the balanced equation. Whenever we use the stoichiometric ratio in the balanced equation, it should give us the most productive ratio. It should give me the most products. And so even if I didn't know the balanced equation, and they may say, like, predict the molar ratio from the balanced equation, we would say, well, it should be most indicative of the ratio that gave me the most product. So that's the most important point on the graph. It's the graph that gives me the most product should be closest to the stoichiometric ratio. Now, it doesn't mean that we have to have the stoichiometric ratio. I mean, this reaction runs at varying ratios. However, here's what I think is kind of cool about this particular setup. So, for example, the copper chloride solution is blue. Well, in this, I guess, graduated cylinder, I used 40 milliliters of copper chloride and 20 milliliters of sodium phosphate. But can you kind of see that, like, that would be a 2-to-1 ratio? And that's not the ratio in the balanced equation. Anytime I use more than approximately 35 milliliters of copper chloride, then that's too much copper chloride. If we say the optimal ratio is like a 3-to-2 ratio, approximately 35-25, I know it's not perfect. But yeah, this one had too much of the blue copper chloride. Now, obviously, there's still precipitate in there. The reaction still happened, but there's excess copper chloride. And what I love about this particular setup is that you can see it. Because the copper chloride is colored, when it's in excess, I can see it. The solution on top is supposed to be sodium chloride, which is supposed to be colorless. And it's not. It's still got a blue tint to it. So then I know that the excess solution was the copper chloride. And the limiting reactant would have been the sodium phosphate. There was not enough. In fact, if I were to add more of the sodium phosphate to this graduated cylinder, I should get more precipitate because there's still some copper in this blue solution. So if I add more phosphate, I should get more copper phosphate precipitate. Here's the optimal ratio. This is the most product, and there's just a little layer on top of clear solution, and that should be mostly sodium chloride. But then all of these, again, I do not have the optimal ratio. I'm supposed to have about 25 milliliters of the sodium phosphate, that 3-to-2 ratio. But if I have more sodium phosphate, then that becomes the excess reactant. So up on top of the precipitate is a clear solution. It's supposed to be sodium chloride, but I bet on top of all of these precipitates is also excess sodium phosphate. Now, because it's colorless, I don't really see anything exciting. But if all of these test tubes still have some sodium phosphate in this clear solution, if I were to add more copper chloride, I should see more precipitate. So a couple things they could ask me about a graph like this. Number one, they could ask me, like, where's the optimal ratio? Where is the ratio that would represent the molar ratio from the balanced equation? I'm just looking for the peak of the graph. Then if I follow that down to find my optimal ratio, if I ever have more of a particular reactant, then that reactant is in excess. And if I have less than the optimal ratio, then that reactant is limiting. Interesting. Okay, so here would be another example. Just another reaction. I didn't do this reaction, but it could have. Here's the reaction of iron nitrate and sodium phosphate. it produces a solution of sodium nitrate, and then it would be really similar to this, but you would get iron hydroxide as kind of a brown precipitate, looks like dirt. This blue is way more beautiful. But if I look at the ratio in the balanced equation, it should be a 1-to-3 ratio of iron nitrate to sodium hydroxide. And so look at that peak. The optimal ratio, if I follow it down, it really should be about a 15 milliliter to 45 milliliter 1-to-3 ratio. It should match the ratio in the balanced equation. And so if 15 milliliters of iron nitrate completely react with 45 milliliters of sodium hydroxide, because that would represent a 1-to-3 ratio, if I ever use more than 15 milliliters of iron nitrate, that would be an excess. If I use less than 15 milliliters of iron nitrate, it's limiting. And I could say the same thing about the sodium hydroxide. If I use more than 45 milliliters, it's an excess. And if I use less than 45 milliliters, it's limiting. So you may not have looked at limiting and excess graphically last year, but conceptually, you probably knew that the optimal ratio should give me the most products. And so if I can find the optimal ratio on a graph, then I should be able to match that to the ratio in the balanced equation. And from there, I can predict limiting and excess. Pretty cool, huh? So if I stop sharing this, and then we go back here, there, so there's another look at them. So there could be a question that might pop up on an assessment at some time that gives you a graphical representation of a reaction. And from that graph, we can figure out the stoichiometric ratio in the balanced equation, and we can figure out if at any other point on the graph we have a limiting excess situation. And then here we can kind of look at it too to see like there's evidence that the copper solution is in excess because it's blue on top. Or here, like this is probably the excess sodium solution because it's colorless on top. Pretty awesome, huh? Maybe, maybe not. But just wanted to kind of show you another example of a graphical representation of limiting and excess.